Section 1 Introduction. We're going to discuss the importance of tracing the origin of content generated by language models. This has become a pressing issue, especially with the rise of AI models that can generate human-like text. For instance, Stack Overflow, a popular website, has banned users from posting answers generated by OpenAI's ChatGPT model to prevent the spread of misinformation. A reliable tool that can attribute text to a specific language model would be beneficial for various individuals, such as platform moderators and teachers, as well as model providers who want to track the use or misuse of their models. To trace the origin of generated content, we use a watermark. This is a signal embedded within the content that indicates its source. In our case, we're dealing with text from a language model. We're considering a scenario where a third-party user sends prompts to a trusted provider, who then generates text from their language model with a watermark. This allows a detector to later identify the source of the text if the user publishes it. A good watermark should meet 3 criteria. It should not distort the original text distribution, it should be detectable without the language model and/or prompt, and it should be robust enough to withstand alterations of the watermark text. Existing watermarks either distort the model's sampling distribution or are not robust to editing or cropping the text. Classical techniques for covertly encoding messages within samples of text from a language model are neither agnostic nor robust. We've developed the first watermarks for attributing text to a language model that meet all 3 criteria. Our approach consists of 2 components: a generate method that maps a sequence of random numbers encoded by a watermark key to a sample from the language model, and a detect method that aligns a suspected watermark text with the watermark key sequence using the shared key. Our watermarks are distortion-free, meaning that each call to generate is equal in distribution to a sample from the original language model. Detecting watermark text is challenging because the detector cannot simply recompute, generate, and compare its output against the text, as they may not know the prompt which produced the text. Our watermarks are easily detectable with a suitable model-agnostic and prompt-agnostic test statistic. To ensure that detect method is robust to edits of the watermark text, we use techniques for robust sequence alignment to align a suspected watermark text with the watermark key sequence. We measure the quality of the alignment using an alignment cost specific to each watermark. This procedure ensures the watermark is detectable even from a small, corrupted block of watermark text within some other larger text. While generate is a deterministic function, if our watermark produced the same text every time for each prompt, it wouldn't be very useful. We've designed a wrapper around generate that calls generate, using a randomly chosen subsequence of the random number sequence instead of generating tokens from the same starting point each time. This doesn't affect watermark detectability. In practice, the effectiveness of our watermarks improves exponentially with the length of the suspected watermark text and decreases only linearly with the length of the random number sequence. By increasing the length of the random number sequence, we can reduce the probability of reusing the same random subsequence while still ensuring our watermark has good statistical power. We've tested our watermarks using the OPT 1.3b, Llama 7b, and Alpaca 7b language models. Across all models, we found the second instantiation using exponential minimum sampling to be the most powerful. For both the OPT 1.3b and Llama 7b models, using this watermark, we can reliably detect watermark text from 35 tokens even after corrupting between 40 to 50% of the tokens via random edits. The watermark also remains detectable from 50 tokens even after paraphrasing the text by translating to French, Russian, and back. For the Alpaca 7b model, we conducted a case study on the feasibility of watermarking responses to typical user instructions. Detection is more difficult due to the lower entropy of the responses, but around 25% of the responses are detectable, and the watermark is also less robust to paraphrasing. We've released code for implementing the watermark and reproducing the experiments in this paper, as well as additional supplementary material including an in-browser demo of the watermark detector. Section Summary. The paper introduces the concept of watermarks for attributing text to a language model. Watermarks are signals embedded within generated content that encode the source of the text. The watermarks should be distortion-free, agnostic, and robust, and the paper presents a methodology that achieves all 3 criteria. Section 1.1 Related Work. In this section, we'll be discussing related work in the field of text watermarking, a specific type of linguistic steganography. The aim here is to embed a hidden message, or watermark, within a block of text. There are 2 main types of linguistic steganography. One involves altering an existing text, and the other involves creating a distribution over a cover text. Unlike steganography, digital watermarking literature has always emphasized the importance of a watermark's resilience to corruption. This means that a text watermark should be able to endure some changes to the text, which rules out the use of many existing linguistic steganography techniques. Historically, text watermarking involved modifying an existing text to incorporate a watermark. However, our focus is on generating watermark text while maintaining the text's distribution from a language model. The concept of generative watermarking is relatively new and has been made possible by recent advancements in open-ended text generation. Some of the pioneering work in this area proposed a generative watermark for machine translation system outputs, which biases the system towards translations with specific features that can be detected later using a hypothesis test. Our work is closely related to a method that watermarks text from a language model by adjusting the token log probabilities from the model at inference time based on a function of the previous K1 tokens, where K is a hyperparameter. There's also an ongoing unpublished work that describes a technique for watermarking language models using exponential minimum sampling to sample from the model, where the inputs to the sampling mechanism are a hash of the previous K1 tokens. However, neither of these watermarks are distortion-free, and our experiments show that the distortions are quite noticeable in practice, such as excessive repetition of certain tokens. Another method proposes watermarking text from a language model by generating the initial few tokens at random and then using these tokens to seed a random number generator to watermark the remaining tokens. This method is similar to ours in that it doesn't cause distortion, but the resulting watermark isn't robust and they haven't empirically evaluated the effectiveness of their watermark. An alternative approach for detecting synthetic text is to use a classifier to distinguish between synthetic and human text. These methods have the advantage of not needing coordination with the original text producer, but their effectiveness depends on the distribution and they don't provide a priori guarantees on the significance level of detection. Lastly, it's worth noting that our context is different from the literature on embedding watermarks in the training data of machine learning models to infer the model's training set or influence the model's output. These watermarks are intentionally not distortion-free, as the goal is to embed a learnable signal in the training data that influences the behavior of models trained on the watermark data. Section Summary. Text watermarking involves hiding a hidden message within a passage of text. Existing approaches fall into two categories: edit-based methods that modify existing text, and generative methods that construct a distribution over cover text. Our work focuses on generative watermarking, specifically on preserving the distribution over the text from a language model, while previous approaches have shown distortions in the watermark text. Section 2. Methodology and Theoretical Analysis. Let's break down the methodology and theoretical analysis of this paper. We're dealing with a language model that maps a string of any length to a distribution over a set of words, or vocabulary. This model predicts the next word based on the preceding string. The process begins with the language model provider sharing a random sequence, known as the watermark key sequence, with the detector. The user then sends a prompt to the language model provider, who generates a text using the prompt and the watermark key sequence. The user can then publish this text, either as it is or after editing it, or they can publish a completely different text. The detector's job is to determine if the published text is watermarked, meaning it depends on the watermark key sequence. The language model provider uses a method called generate to create text. This method uses a decoder function that takes an element of the watermark key and a distribution over the next token to predict the next token. The prediction should be a sample from the distribution. The paper defines a decoder as distortion-free if it satisfies a certain condition. This condition is that the probability of the decoder predicting a certain token given a distribution is equal to the probability of that token in the distribution. The paper also discusses a lemma, which states that the only difference between using the generate method and sampling directly from the language model is that the watermark key sequence is an input to the method rather than being resampled within the method for each call. The detector uses a method called detect to compute a p-value, which is a measure of the strength of evidence against the null hypothesis that the published text is not watermarked. The p-value is computed using a permutation test with a certain number of resamples. If the p-value is small, it suggests that the text is likely watermarked. The goal is to design a test statistic such that the p-value will typically be small if the published text is watermarked. This involves identifying an alignment cost, which measures the quality of a match between a subsequence of the input text and a subsequence of the watermark key. The paper also provides an example with a binary vocabulary to illustrate how the decoder and the alignment cost work together. In this example, the language model provider generates a binary text from the model using a certain decoder. The alignment cost is defined as the absolute difference between the binary text and the watermark key sequence. Finally, the paper discusses a solution for avoiding reusing elements of the watermark key sequence across queries. This involves making the generate method stateful, which allows the language model provider to generate multiple independent watermark text samples from the language model. Alternatively, A randomized wrapper around the generate method can be used, which randomly shifts the watermark key sequence before passing it to the generate method. Section summary. In this section, the authors describe the methodology and theoretical analysis of their watermarking protocol. They introduce the autoregressive language model, which generates text based on a given prefix and a distribution over the vocabulary. The protocol involves the LM provider sharing a random watermark key sequence with the detector, the user sending a prompt to the LM provider, the LM provider generating text based on the prompt and the watermark key sequence, the user publishing the generated text, and the detector determining if the published text is watermarked. The authors also discuss the distortion-free decoder, the alignment-based detection strategy, and the randomized wrapper for generating multiple independent watermark text samples. Section 2.2 Terminology, Watermark Strategies and Watermark Potential. From now on, we'll use the term watermarking strategy to describe a specific application of the shift generate, and detect methods. This involves defining the internal parameters of both algorithms, such as the decoder gamma, the test statistic phi, and the watermark key sequence distribution nu. We'll provide examples of watermarking strategies in the upcoming sections. For each strategy, we'll demonstrate two main points. First, that the decoder doesn't distort the original message, and second, that the likelihood of detecting watermark text is high, depending on the length of the text and the watermark key sequence. It's important to note that the non-distortion of the decoder is crucial for our main arguments. The second point is intended to give you an idea of when we'd expect the detector to be powerful enough and to prepare you for the experimental results we'll present later. The strength of the likelihood of detecting watermark text depends on the observed token probabilities of the text, which we'll refer to as the watermark potential. Let's define the watermark potential. It's a measure of how much the text deviates from a deterministic language model. If the language model is deterministic, the watermark potential is 0. But if the model has high entropy, the watermark potential approaches 1. The ability of the detector to reliably tell the difference between watermarked and unwatermarked text depends on the watermark potential of the language model. For instance, if the language model is deterministic, any watermark that doesn't distort the text will have 0 statistical power. We'll formalize this idea by establishing a lower limit on the detection accuracy of any watermarking strategy, based on the watermark potential of the original language model. Specifically, we'll set a lower limit on the error of any classifier that tries to distinguish between watermarked and non-watermarked text, given some watermark key. We're not making any assumptions about the distribution of the watermark key, except that it's independent of unwatermarked text. We'll present a lemma, or a proven proposition, that supports this idea. This lemma suggests that it's impossible to distinguish between watermarked and non-watermarked text that are identical in distribution, i.e., distortion-free, if the text typically has low watermark potential, regardless of the design of the watermark key. In other words, the sum of the type 1 and 2 error rates of the classifier will be close to 1 if the watermark potential is close to 0. However, this theorem isn't perfect. Depending on the language model, its result may not be meaningful for small values of a certain constant, circa. This is because only texts whose token likelihoods all exceed a certain value contribute to the lower limit. Also, our upper limits scale inversely with the square of the watermark potential, which will always be smaller than the watermark potential itself since the watermark potential is bounded between 0 and 1. In the upcoming sections, we'll establish the existence of test statistics for each watermark that improve exponentially with the length of the text and decrease at most linearly with the length of the watermark key sequence. The test statistics we use to prove these upper limits differ slightly from those we use in our experiments. In the former case, we prioritize the simplicity of stating the limits in terms of watermark potential, while in the latter case, we prioritize empirical performance. Section summary. In this section, the authors introduce the concept of watermarking strategies as concrete instantiations of the shift generate, and detect methods. They provide concrete examples of these strategies and prove that the decoder is distortion-free. They also establish upper bounds on the p-values of watermark text, which depend on the observed token probabilities and are referred to as the watermark potential. The authors emphasize that the detection accuracy of any watermarking strategy is lower bounded by the watermark potential of the original language model. The p-value upper bounds for the watermarking strategies aim to show that the statistical power of the watermark improves exponentially with the length of the text and decays at most linearly with the length of the watermark key sequence. Section 2.3 Watermarking via inverse transform sampling. We're going to discuss a method of watermarking using a technique called inverse transform sampling. This technique allows us to sample from a single variable distribution by using a uniform random variable and its inverse cumulative distribution function, CDF. The beauty of this method is that it works regardless of the order of the CDF. We're going to use this property to create a watermarking strategy where the generation process doesn't distort the original data and the detection process is unbiased. In our approach, the generation process uses a decoder that maps a sequence of uniform random variables and permutations to tokens using inverse transform sampling. To detect if a text is watermarked, the detector checks the correlation between the sequence of permuted indices of the tokens in the text and the sequence of uniform random variables. If the text is not watermarked, the sequence of permuted token indices will be uniformly distributed regardless of the text itself, and thus won't correlate with the sequence of uniform random variables. To explain this formally, let's consider pi as the space of permutations over the vocabulary n, and for xi equals u, pi, in 0, 1, times pi equals xi and any distribution mu in delta n, we define the decoder by gamma, xi, mu. This is the token with the smallest index in the permutation pi such that the CDF of mu with respect to pi is at least u. We can show that this decoder is distortion-free. We have a theorem that supports this. Let pi in pi be arbitrary and let u be a uniform random variable in 0, 1, with xi equals u, pi. Then gamma is distortion-free with respect to xi. The proof of this theorem shows that for any mu in delta n and y in n, the probability that gamma, mu, xi, equals y equals mu, y. This is because gamma, mu, xi, equals y if and only if u lies in a certain interval whose width is exactly mu, y. After establishing that the inverse transform sampling decoder is distortion-free, we move on to analyze the detectability of the watermark. For convenience, we define a normalization function eta that maps n to 0, 1. Similar to a simple example, the sequences eta, pi underscore I, y underscore I equals 1, caret m, and u are correlated. For analysis purposes, we define an alignment cost function d that measures the negative covariance between each u underscore I and eta, pi underscore I, y underscore I, both of which have an expected value of 1/2. We then characterize the difference in the expected value of our alignment cost on some text, assuming the text is watermarked versus not watermarked in terms of the watermark potential of the text. We define a constant c underscore 0, which is the variance of eta when applied to a uniform distribution over n. Note that c underscore 0 is approximately 1/12. We have a lemma that states that for any given generation length m and watermark key length n, where n is greater than or equal to m, the expected difference in alignment cost for watermark text and non-watermark text is proportional to the watermark potential of the text. This implies that watermark samples with watermark potential not close to 0 will have exponentially small expected p-values with respect to the length m of the text. The bound grows only linearly with the length n of the random number sequence. This means that for moderately large m, a language model provider can generate a lot of distortion-free watermark text while still enabling detection of the watermark from snippets of m tokens. However, the computational complexity of detection scales linearly with n, which in practice may be a more relevant limitation than the statistical power of the watermark. Both the detection process and the test statistic are easily parallelizable. Section summary. The section discusses watermarking using inverse transform sampling, which is a technique for sampling from a distribution by using the inverse cumulative distribution function. The authors propose a watermarking strategy that is distortion-free and agnostic, where a decoder maps uniform random variables and permutations to tokens using inverse transform sampling. The watermark is detected by correlating the sequence of permuted indices of the tokens with the sequence of uniform random variables. Section 2.3.1 Robustness to substitutions, insertions and deletions. We're going to discuss how our method remains effective even when the original watermark text is tampered with by changing, adding, or removing tokens. First, let's talk about token substitutions. We've found that even if most of the tokens in a watermark text are replaced, it's still possible to detect the watermark as long as the remaining tokens have a watermark potential that's not 0. This is because the original tokens still correlate positively with the random variables from the watermark key sequence, while the replaced tokens show a small negative correlation. To deal with added or removed tokens, we've adjusted our test statistic to include a soft version of edit distance, which measures how many changes are needed to turn one string into another. This is done by incorporating an alignment cost into our original alignment cost. This cost is assigned to each addition and deletion operation when aligning the tokens with the sequence, while the base alignment cost defines the quality of the alignment via a cost function over substitutions. We've also defined a Levenstein cost, which is a measure of the minimum number of single-character edits, insertions, deletions or substitutions, required to change one word into the other. This cost is used to redefine the test statistic, ensuring that our detection method is robust not only to substituting tokens, but also to inserting and deleting tokens from watermark text. Next, we've defined an edit distance, which is equivalent to the minimum number of insertion and/or deletion operations needed to transform one string into the other. We've found that there must exist a substring of the tampered text within a certain edit distance of a substring of the original text that the detector will be able to identify as watermarked. However, the number of strings within a certain edit distance of an original block of watermark text increases exponentially with the edit distance. To ensure we can detect the watermark, we must set a certain parameter, gamma, to be proportional to the inverse of the edit distance. This means our bound on the expected p-value becomes meaningless as soon as the edit distance is proportional to the inverse of the logarithm of the block size. In practice, we've found that smaller values of gamma perform significantly better. One takeaway from this is that using a block size smaller than the length of the input text for detection can be an effective strategy when the text has been significantly tampered with. The assumption that the block size divides evenly into the length of the input text is not important in practice. Section Summary. The section discusses the robustness of the watermark detection algorithm to substitutions, insertions, and deletions in the watermark text. Lemma 2.5 shows that even if an adversary replaces most of the tokens in the text, detection is still possible as long as the remaining tokens have a non-zero watermark potential. To handle insertions and deletions, the test statistic is modified using a soft notion of edit distance, as defined in definition 3. Lemma 2.6 demonstrates that the detector can still distinguish the watermark even if the corrupted text is within an edit distance of epsilon m from the original text, with a bound on the expected p-value. Section 2.3.2 What we run in practice. In the section titled, What we run in practice, the authors discuss the practical implementation of their watermarking strategy. They explain that to minimize overhead, they use a single random permutation instead of a full sequence. This means that the permuted token indices of both watermarked and non-watermarked text are no longer conditionally independent of each other. This could potentially affect the results of certain mathematical proofs, but the authors note that they have not observed any decrease in statistical power in practice. Furthermore, they emphasize that regardless of these mathematical proofs, the p-values from the detection process are still valid. This is because they are constructed in a way that does not rely on the distribution of the permutations. Therefore, the watermark remains distortion-free. The authors also discuss the use of a test statistic, which is a measure used to quantify the degree of alignment between the watermarked and non-watermarked text. They find that using the absolute difference between the permuted token index and a function of the original token index as the alignment cost performs better empirically than the alignment cost used in a previous equation. They then introduce two versions of their watermarking strategy, the ITS version and the ITS edit version. The ITS version uses the decoder from a certain equation, the test statistic from a specific algorithm, and the watermark key distribution as the uniform distribution over a certain range. The ITS edit version is similar, but it defines the test statistic using a simplified version of the Levenshtein cost, which is a measure of the difference between two sequences. In summary, the authors have developed a practical implementation of their watermarking strategy that uses a single random permutation, a specific test statistic, and a uniform watermark key distribution. They have also introduced a variant of this strategy that uses a simplified version of the Levenshtein cost. Despite some potential theoretical concerns, they have found that their approach works well in practice. Section Summary. In practice, we use a single random permutation to reduce overhead in both the generation and detection processes. Despite the fact that the permuted token indices of watermarked and non-watermarked text are no longer conditionally independent, we observe no degradation in statistical power. The p-values from the detection process remain valid, regardless of the test statistic used. Section 2.4 Watermarking via exponential minimum sampling. We're suggesting a method to embed watermarks into text using a technique called exponential minimum sampling. This technique maps variables within a range of 0 to 1 to tokens in a vocabulary. Unlike other methods that introduce distortions, our approach ensures that the watermark text remains distortion-free and robust. To explain this in simpler terms, we define a decoder that takes two inputs, a set of variables and a set of probabilities. The decoder then finds the token that minimizes the negative logarithm of the variable divided by its corresponding probability. We've proven that this decoder doesn't distort the original text, but we've saved the details of this proof for the appendix. We also introduce a concept called the alignment cost, which is a slight modification of a previously proposed idea. The alignment cost is calculated by summing up the negative logarithms of the variables associated with each token in the text. This cost helps us measure the difference between watermarked and non-watermarked text. We've also defined a test statistic, which helps us quantify the difference in alignment costs between watermarked and non-watermarked text. We've proven that this difference is equal to the watermark potential of the text, but we've saved the details of this proof for the appendix as well. We've also shown that the expected difference in alignment costs between a watermarked text and a non-watermarked text is equal to a certain function of the text. This result holds true for any subset of the text. Finally, we've proven that the probability of the test statistic for a watermarked text being less than or equal to that for a non-watermarked text is less than or equal to a certain function of the text. This result holds true for any subset of the text. The details of this proof are also saved for the appendix. Section summary. The paper introduces a watermarking technique using exponential minimum sampling to map variables to tokens, enabling distortion-free and robust watermarking. The decoder is shown to be distortion-free, and the expected values of the alignment cost on watermarked versus non-watermarked text are characterized in terms of the watermark potential. The p-value output by the detection algorithm is upper bounded using a concentration argument. Section 2.4.1 Robustness to Corruptions. We're going to discuss two main topics: the robustness of our watermarking method to text corruption and the practical application of our method. In terms of robustness, it's challenging to provide a high probability upper limit for the corruption of watermarked text. This is mainly because the elements in the alignment metric, which we use to measure similarity, are not limited. Therefore, each substitution or insertion operation can significantly influence the test statistic, requiring careful analysis. We could adjust the alignment metric to limit the influence of each operation, but we won't do this as it's not crucial to our main argument. In practice, we use a slightly modified version of the alignment cost, which we found to perform better. We refer to this version as Express, and a version that uses the Levenstein cost as Express Edit. For both versions, we use a uniform distribution over a sequence of length n as the watermark key distribution. The only difference between Express and Express Edit is that the latter uses the Levenstein cost to define the test statistic. We tested our watermarking strategies, its edit, express, and express edit, on the OPT 1.3b and Llama 7b models. We also ran experiments using the generate method for reproducibility. We tested all watermarks using a block size equal to the length of the text. We generated watermarked text continuations of prompts sampled from the news-like subset of the C4 dataset. We varied the generation length and the random number sequence length, and reported median p-values of watermarked text over 500 samples. We also tested the robustness of our method to 4 types of paraphrasing attacks: random substitution, insertion, deletion of tokens, and translation from English to French and back. The first 3 attacks allowed us to vary the level of corruption systematically, while the last attack is an example of a real-world attack. We conducted a case study on the feasibility of watermarking the responses of a language model to user queries. We found that our distortion-free watermarks produced better responses than hashing-based watermarks for certain types of instructions. We also compared our watermarking method with a baseline method, which is not distortion-free. We used the detect method to report p-values for all watermarks. We reported error bars for the median p-value based on a bootstrapped estimate of the standard deviation using 1,000 resamples. In summary, we found that our watermarking method is robust to various types of text corruption and performs well in practice. We also found that our method produces better responses than hashing-based watermarks for certain types of instructions. Section summary. The section discusses the challenges of bounding the influence of corruptions on watermark text and the modification of the alignment cost in practice. The experimental results validate the statistical power of different watermarking strategies and evaluate their robustness to various paraphrasing attacks. Additionally, a case study is conducted on the feasibility of watermarking language model responses, highlighting the importance of distortion-free watermarks. Section 3.1 Varying Text and Watermark Key Length. In this section, we experiment with different lengths of watermark text, while keeping the watermark key length constant at 256 for all our watermarks. We also set specific values for gamma, a tuning parameter, for our its and express watermarking methods. Refer to the appendix for more details on how we tuned gamma. Our findings show that our its watermarks perform slightly better than the KGW 1.0 method, while our express watermarks perform slightly better than the KGW 2.0 method. Interestingly, both KGW methods distort the text distribution, yet our methods still outperform them. We also found that our express watermarks are more effective than our its watermarks, as they require about 2 to 3 times fewer tokens to achieve a similarly low median p-value. However, one potential advantage of the its watermarks over the express watermarks is that they have less overhead. The watermark key for express and express edit is a sequence of n vectors, each with a size equal to the vocabulary size, while for its and its edit, it's simply a sequence of n numbers between 0 and 1. All our watermarking strategies performed worse on the Llama 7b model than the OPT 1.3b model. This is because Llama 7b typically generates text with lower entropy than OPT 1.3b. We also noticed that the median p-values for the KGW 1.0 and KGW 2.0 watermarks can be unstable, especially for smaller lengths of watermark text. This instability is due to the discrete nature of the test statistic, which is the number of tokens in the text that belong to a green list versus a red list. We also experimented with varying the length of the watermark key sequence for different lengths of watermark text from the its and express watermarks. As our theory predicted, the p-values of watermark text increase linearly with the length of the watermark key sequence. However, this rate of growth is quite mild and decreases rapidly with the length of the watermark text. Even for a watermark key sequence length of 4096, which is larger than the maximum generation length of both the OPT 1.3b and Llama 7b models, a slight increase in the number of tokens is enough to distinguish watermark text with roughly the same statistical power as a watermark key sequence length of 64. Section Summary. In this section, the authors discuss their experiments on varying the length of watermark text and the watermark key. They find that their its watermarks slightly outperform the KGW 1.0 method, while their express watermarks outperform the KGW 2.0 method. The express watermarks are more powerful and require fewer tokens to achieve a low median p-value. However, the its watermarks have less overhead as their watermark key is simpler. All watermarking strategies perform worse on Llama 7b compared to OPT 1.3b due to the lower entropy of Llama 7b text. The p-values of watermark text increase linearly with the length of the watermark key, but the rate of growth decreases with the length of the watermark text. Section 3.2 Robustness to Corruption and Paraphrasing. We're now going to assess how resilient our watermarking methods are to different types of corruption and rewording. We'll be focusing on our most robust watermarks, referred to as express and express edit, and comparing them to a watermark known as KGW 2.0. We'll discuss the results for other watermarks later in the appendix. As we increase the value of n, the computational effort required to calculate our test statistics also increases. However, the impact of a larger n on statistical power is minimal, as shown in one of our figures. Therefore, we've decided to conduct all our experiments with n set to 256. This value is large enough to ensure that the watermark text in all our experiments remains distortion-free. If we reduce the penalty for insertions or deletions, referred to as gamma, we can improve robustness, but only up to a certain point. This is because reducing the penalty for edits effectively increases the number of possible alignments, which can negatively impact the statistical power of the its edit and express edit watermarks when n is large. We've decided to use the same gamma values for its edit and express edit as we did in the previous section. We'll discuss how we fine-tuned gamma later in the appendix. We've also experimented with varying the percentage of substituted, inserted, and deleted tokens. For the insertion experiment, we only gave the first m tokens to the detector. For the deletion experiment, we initially generated more than m watermark tokens to ensure that we still had at least m tokens left after deleting some. Our express and express edit watermarks are equally resilient to substitution errors. However, express edit is significantly more resilient to insertion and deletion errors. We've compared our watermarks to the most robust version of KGW 2.0, which only uses the previous token to determine the next token distribution. This biases the distribution towards a subset of bigrams. If we were to use more than one previous token, any substitution would disrupt the watermark signal in a particular token, reducing the statistical power of their watermark. We've also conducted a roundtrip translation attack, where we tried to reword watermark texts of varying lengths by translating them into another language, French and Russian, and then back into English using a machine translation model. We found that using Russian was a more effective attack than French. None of the watermarks, except for express edit, were able to reliably detect watermark text with a probability of less than 0.05, regardless of the value of m. In many cases, both French and Russian translations still preserved large parts of the original text, which was enough for watermark detection even using express, which is less resilient to insertion and deletion errors than express edit. We didn't verify whether the round-trip translations preserved the basic meaning of the original text, so our results might be overly pessimistic about the resilience of our watermarks to these attacks. It's also possible that using different machine translation models or other forms of automated rewording could be more effective in evading watermark detection. We're making all our watermark generations for each watermarking strategy available, along with their translations, as part of our code release. Section Summary. In this section, the authors evaluate the robustness of their watermark strategies to different forms of corruption and paraphrasing. They compare their strongest watermarks, Express and Express Edit, against KGW 2.0 and find that Express Edit is more robust to insertion and deletion errors. They also conduct a round-trip translation attack using machine translation models in French and Russian, and find that Express Edit is the only watermark that reliably detects watermark text in both languages. Section 3.3 Case Study. Instruction following. We're now going to discuss a case study that focuses on how users typically interact with language models. Most often, users give the model a command, such as, "Give me code for." The most popular language models, like ChatGPT, are specifically designed to respond to these types of instructions. In this case study, we're using the Alpaca 7B model, which has been fine-tuned to follow instructions, to examine how effective watermarking is for a model that follows instructions well. We've taken 200 instructions from the Alpaca 7B evaluation dataset and generated watermarked responses of up to 200 tokens for each. We then calculated conditionally valid p-values for each response using the original version of the detect function with t set to 500. We also repeated the round-trip translation attack from experiment 6. We've made all the watermark generations for each method, along with their translations in the instruction prompts, available as part of our code release. We've also plotted the distribution of p-values for the Express Edit and KGW 2.0 watermarks, as well as the p-values versus the watermark potential of the watermark text. In general, the Alpaca 7B responses have a significantly lower per-token watermark potential than both the OPT 1.3b and Llama 7B models. This means that our watermark's statistical power is weaker, even though the responses are usually longer than in previous experiments. Specifically, based on a random sample of 200 prompts, the average per-token watermark potential of text from Alpaca 7B is 0.28, compared to 0.59 for Llama 7B and 0.67 for OPT 1.3b. Unlike in previous experiments, KGW 2.0 outperforms the Express Edit watermark. This difference in performance is largely due to KGW 2.0 distorting the text distribution and producing responses with a noticeably larger watermark potential than regular responses from the model. For responses where the unnormalized watermark potential, i.e., watermark potential multiplied by the number of tokens in the response, to account for varying response lengths, is roughly 60 or more, both watermarks tend to yield p-values close to 0. However, paraphrasing the responses via round-trip translation attacks into both French and Russian weakens the statistical power of both watermarks. It's important to note that our watermark doesn't use hashing of previous tokens to determine the distribution of the next token. To illustrate the problems with hashing, we created a version of the watermark that uses the previous k tokens to seed a random number generator instead of using the watermark key. We call this version Express Hash. We then prompted Alpaca 7B with requests for various types of lists. Because Alpaca 7B tends to separate items in lists by the same recurring token, such as a comma or a newline character, and because this recurring token determines the next token, for k equals 1 the lists degenerate into repetition. Hashing with k greater than 1 significantly improves the quality of samples. However, even using k equals 4 can sometimes produce noticeably repetitive text. We want to emphasize that while increasing k may improve sample quality by making the distortions of watermark text less noticeable, it also harms the robustness of the watermark. For example, replacing just 20% of the tokens would be enough to evade detection for k equals 4. Furthermore, using a more robust hash function doesn't avoid this trade-off between robustness and distortion-freeness. There's a direct trade-off between the likelihood of a hash collision and the robustness of the hash. In addition to the above, we've included more examples, for both k equals 1 and k equals 4, and different prompts in the appendix in our code release. Section Summary. In this case study, we evaluate the effectiveness of watermarking a language model that follows instructions. We use the Alpaca 7B model and generate watermarked responses based on 200 instructions. The watermark potential of the Alpaca 7B responses is lower compared to other models, and the KGW 2.0 watermark outperforms the Express Edit watermark. However, when we paraphrase the responses using round-trip translation attacks, both watermarks lose their statistical power. We also explore the limitations of hashing previous tokens to determine the distribution of the next token and find that increasing the value of k improves sample quality but harms the robustness of the watermark. Section 4 Discussion. In this discussion, we present the first ever watermarking techniques for language models that remain intact even after editing or cropping. Our approach is based on the concept of using robust sequence alignment methods to align a potentially watermarked text with a watermark key sequence. This key sequence is used by the language model provider to create watermark text. The effectiveness of our watermarks increases exponentially with the length of the text and decreases linearly with the length of the watermark key sequence. The computational complexity of our watermark detection algorithms is directly proportional to the length of the watermark key sequence, which is also the total number of distortion-free watermark tokens that the language model provider can create. In contrast, the complexity of the watermark detection algorithms of other methods is directly proportional to the length of the input text. However, these watermarks are either not robust to corruption or not distortion-free. Whether this apparent trade-off is fundamental or not is an intriguing question that remains open. All the watermarking strategies, including ours, assume that the language model provider and the watermark detector share information beforehand, such as a watermark key. The main limitation of watermarking is that the detector must trust the language model provider to apply the watermark correctly when generating text. Another limitation, which is not inherent but currently applies to all known watermarks, is that the language model provider cannot release the model weights. If they did, users could simply query the model directly, bypassing the language model provider. Embedding robust watermarks directly into the weights of a language model without compromising the model's quality is an important area for future research. Recently, several major language model providers, including OpenAI, Anthropic, Google, and Meta, have committed to watermarking the text from their models. We have a few recommendations for practitioners. Firstly, we suggest using our Express Edit watermark, as it is the most robust watermark we have tested. Secondly, although the length of the watermark key sequence, which limits the total number of distortion-free watermark tokens that the language model provider can create, can grow almost exponentially with the block size of the test statistic, we find that using a relatively small watermark key sequence, for example, n equals 256, does not significantly affect the quality of the watermark text. Our watermark detection procedures, including both the detect function and the test statistic from the algorithm, can be easily parallelized. Therefore, even with a very large watermark key sequence, for example, n equals 10000, we don't expect the computational demands of watermark detection to be a significant bottleneck. However, we should note that we have not tested such large n values with our implementation, and we did not take advantage of parallelism. Section Summary. The paper introduces distortion-free watermarking strategies for language models that are resistant to editing and cropping. By leveraging robust sequence alignment methods, the proposed approach aligns watermark text with a watermark key sequence, resulting in exponentially improved statistical power and linear computational complexity. However, the limitations include the need for trust between the LM provider and detector, as well as the inability to release model weights. Future work should focus on embedding robust watermarks directly into language model weights without compromising quality.